Welcome everyone. Today we're going to continue with our triple integrals, right? Finding the integral through a 3D space, right? Integrating with respect to x, y, z. Okay, trying to find that function acting on that volume of space between two surfaces. Okay, but now depending on the functions, depending on the orientation and how some of those surfaces that we're using to enclose our region through which we're integrating, it may be beneficial to use a different coordinate system, right? Just like we talked about our double integrals in polar form, now we're going to talk about our triple integrals using cylindrical coordinates. Okay, so let me start to share the document can, and we'll start to work through that discussion. All right. All right, so now we're doing triple integrals in our cylindrical coordinate system, right? So before, with our Cartesian or those rectangular coordinates, right, that rectangular coordinate system, when we dealt with our integral, we were describing if we had some space between two surfaces, right, wanting to integrate within that space, we would want to find, right, this triple integral throughout that region E, and most often we'll have some function of x, y, z that's acting on, that's going through, that's dealing with this region, okay? And we're going to deal with that dv, right, that little block of volume that will shift throughout, integrating throughout that entire three-dimensional space. And that's where we saw that dv can take any of those 6 permutations as we start to shift, reorganize, rearrange, which variable we may want to integrate with respect to first, second, third, so on. Okay, and we had done that work in that previous lecture. So now, as we had talked about, in some cases, it may be easier to use a different coordinate system to evaluate, compute that triple integral. Okay, and so kind of, again, thinking back, with our double integrals over kind of those circular regions, circular domains, right? We had talked about the case when perhaps our region over which we are integrating, that kind of circular band, or it could be a full circle, so on, right? We talked about using polar coordinates. R's and thetas. Where instead of using those x and y, we converted those little blocks so that our dA, instead of dx dy, became that r dr d theta, or r d theta dr, how we want to organize. And we had those conversions where x was equal to r cosine theta, y is r sine theta, a way of rewriting, reorganizing. Okay. X squared plus y squared was equal to r squared, so on. We had built that up. So now, with that in mind, we're going to apply that with our three-dimensional system. Okay. So with that said, in 3 dimensions, we can look to the cylindrical coordinates, where we're going to maintain that z axis, that z direction, okay? But now instead, when we start to locate these points out here in space, okay, what we kind of instead do is that we can find this value theta going from, again, that positive x-axis, that theta equaling 0. This would be theta equaling pi over 2, the y-axis, 90 degrees, right? And going counterclockwise. We can find the theta. We can likewise find that distance r, that radial distance from the origin out, thinking about projecting that point down. The z still giving us, right? So we get, instead get this point at r theta z. Instead of x, y, z, to get that location, now we can convert to r theta z. And we still have that same organization. We can still see that x is equal to r cosine theta, y is equal to r sine theta. We're keeping z the same. And one thing I'll mention, unfortunately, I don't think our textbook has that many great examples or problems, but we don't necessarily have to make it so right, depending as we start to see how we're going to work through these cylinders. And maybe we'll say that y is equal to r cosine theta, z is equal to r sine theta, and then x stays the same, right? The way we orient, the way we kind of build later those columns of volume, we can orient, we just have to keep track of how we're rewriting, converting those original Cartesian x, y, z coordinates into the cylindrical format, right? But what we're kind of imagining then is that instead, we'll look at an example. That what if we were trying to kind of work with finding this volume okay, or not volume, but this integral through this kind of cylindrical symmetric region, right? Suppose this was our region E that we wanted to integrate some function throughout. So where we'd have now some little block of volume again, working throughout that space, okay? And if we start to build up those limits of integration, dealing with x, y, and z, getting those kind of boundaries for what x is going to do, what y is going to do, is going to be a little bit difficult as we start to work around that arc, right? Because then, right, x has to go from this inner curve to the outer, or inner curve to outer curve. Same thing for the y, getting those in terms of x and y, so on. can be difficult. So instead, if we can kind of produce a way of identifying that R, that theta, Z staying the same, it's going to be much easier for us then. Okay, I can go from the radius being 1 to 3 or whatever it might be, the theta going from 0 to pi over 2, 0 to pi. Those limits, those identifications are going to be much easier than having to deal with the X, Y, and Z in these kind of curved formats, right? So depending on the region where you're integrating, how to work on those, it may be better, it may be best to switch from those typical, where we might feel more comfortable, X, Y, and Z, into a different coordinate system. In this case, with cylindrical, kind of getting a circular form for that base part of it, and then keeping the height, the Z, the same. Okay, so our R's, theta, Z's working together. All right, but now, just like we had changed, right, just as we had altered our increment of area for double integrals, back in section 15.3 of our text, we do the same for our triple integrals, for dv in our triple integrals. Okay, and so thinking about that little block of volume, now with this space, I know it might be a little bit tedious to see. I think the textbook has a good image. This is on page 1082. Now our little block of volume, notice there's a little bit of arc to it, sweeping through that space. It's not just a rectangular prism, it has a little bit of arc to it. And that's just like we did in polar form. So sometimes I'll get a little bit lazy with my language, or I just won't be as precise, and I might call the cylindrical form my polar form for 3D, okay? But we have our cylindrical coordinates using that same type of arced look. Let's get that solid, dotted, that we had with our polar form. So what we can see is that our dz, the height component, is going to stay consistent. But now, as we start to work through here, this little portion's my little change in the radius, how wide we are. And now the interesting one, this part, that dimension, again, we're trying to make these as tiny as possible, so those little minor differences aren't going to be huge, whether we're at the inner or the outer portion. But recall, based on that arc length formula, this was that r d theta. So we still get that factor of r showing up. But what we start to see is that dv, we can write as that r dr d theta dz. And we can rearrange these in any order. We can put the d theta first, dr in the middle, dz at the end, dz first. But the important piece here is that when we create that dv, we must include this factor, that component of r. And then we can rearrange accordingly. And again, that description, pretty much following what we had done with our work in polar coordinates back in section 15.3. Okay. All right. So with that said, let's look at an example. I'm going to borrow from the book here. Put this down. Let's check out this problem, problem number 18 on page 1083. And we want to evaluate this triple integral over E, Z, dV, where E is the, or E, sorry, is the region enclosed by the paraboloid z is equal to x squared plus y squared, and the plane z is equal to 4. Okay, so this is, like I mentioned, we're at the kind of, now that we start to get into that graphing a little bit more. It doesn't have to be perfect. We just have to be better about getting an idea on what these graphs, these regions, will be. All right, so with that said, we have this paraboloid. I guess I'll do that in blue. Z equals x squared plus y squared, right? So if we start to think about those traces, if x is 0, z is equal to y squared. So we get a parabola open upward, right? All positives there in that direction. If y is 0, z equals x squared. So we get a parabola opening in this direction, right? So far we're going to have this paraboloid. And again, it's not a great picture here, but bear with me. Yeah, that's paraboloid. And then we're going to have this plane as well. So at z equals 4, we're going to have this plane kind of chopping through, right? So again, it's not a perfect picture, but let's go over here. I have my paraboloid where we have it topped off with that plane. So that's my z equals 4. And then below it, we have our paraboloid. We have this bowl, this cup, and we're integrating inside of that space. Okay. So in this case, thinking about that, okay, we're going to be dealing with that region E inside of there. We're going to be integrating throughout. So this is when those kind of columns, those little blocks that fill that space come in. That's where I kind of start to imagine, all right, if I'm going to fill that space along its edge, right, I'm going to get this little piece here. That's going to be one of my columns. So we can shift that anywhere in the space, right? Somewhere place else is going to be a little bit lower. But we're going to get that kind of volume. And then incrementally inside of that, we're going to get our little blocks. There's our little DV. Okay, so thinking about these components, filling with the columns, chopping those up, and that's what we're going to be integrating throughout. Okay, and so when we start to think about, right, these traces, these level curves in that ZY plane, as we had talked about, this would be that curve, Z is equal to Y squared, right? And this is when that issue comes in, because now if I was to think about doing my volume, my area in that space, here, notice, we're going to use the same curve for that lower and upper bound. For Y, which back in 28, we're trying to find the area between two curves, between inside of space. That would be an issue. We'd have to kind of separate and think about, okay, what can I use for this side? What can I use for the other side? And the same thing goes if I had that ZX plane. Okay. So instead, and again, looking at the fact that we have that kind of circular x squared plus y squared, that looks like an equation for a circle, right? Each of those cross sections is a circle. Instead, this will be a prime opportunity we can use cylindrical coordinates for our integral, right, for that region. Because now, as we start to work on that, and again, I'm going to do my best to kind of draw this in. I could probably make it a little bigger, but here we go. When I start to think about my little column of volume to fill, now instead what I can do, I can locate that position of my column with an r theta, and then again, that's going to be my height in z. But I can locate that particular location of my column wherever I happen to be with its r. How far out am I? Close to the z-axis, close to the origin? Am I further out? I can use that radius to tell me where am I along. Am I along the x-axis, y-axis, negative x-axis? That theta can show me that information. Okay. So in this case, let's go back to it. If we're integrating over the region E, z dv, okay, here, if this function had dealt with x and y, we'd have to make that conversion, but there's only z, so z stay the same. We have to remember x equals r cosine theta, y equals r sine theta. Make those substitutions into your function as necessary. But let's think about that region E, right? E was that region inside the paraboloid. Z equals x squared plus y squared under the plane, z equals 4. So with that already, this is kind of identifying that for our z is going to be between x squared plus y squared and that constant 4. Let me remember this other conversion, x squared plus y squared equals r squared, because now notice here, x squared plus y squared, that's r squared. So in this case, we actually see that z depends on our radius squared for that lower limit. We want to make that conversion. Okay, so use that information to make conversions as necessary. We want everything in terms of r's, thetas, z's now. Anytime I see an x and y, I have to make that switch, that change. Okay? All right. So with that said, let's think about our r's and thetas. Okay? So again, working on that piece, in this case, in that span, it would go better. What I want to mention, that for our theta component, we go completely around, right? We're going the full span of that paraboloid. So we go completely around the coordinate system. So in that case, my theta goes between 0 and 2 pi. R, let's think about our R, okay? For that R, and this is sometimes can be a little bit tricky, but we think about, okay, where can I put, in terms of radius, where can I put those little columns of space? I can put it right there on the z-axis, right, when R equals 0, or we can start to shift it out to those edges, right? And if we're going out to z equals 4, okay, if this is our plane, z equals 4, where is that going to meet? Z equals x squared plus y squared, or z equals r squared. When are those two going to be equal? One of those z is going to be the same when r squared equals 4, or when r is equal to 2. So in this case, our value for r can go between 0 and 2. Right now, that radius piece might be a little bit different from what I think going before, but again, equating where are these two curves, where are those two surfaces going to meet? X squared plus y squared equals 4, right? Or x squared plus y squared is r squared equaling 4, r must be 2. So we go from 0 being that inner point all the way out to r being 2. Take some time to look that through, consider that in that space, because now our integral becomes that still z, but now instead of dv, remember that's when we're going to get our factor of r. And now let's think about these components. Z depends on r, so I want to make sure to do z before I integrate with respect to r, right? So let's do z right away. My dz goes from lower r squared to 4. That factor of r we needed in creation of that dv we talked about before. But now for the r and theta, they're both just constants, right? So we can put those in any order. Let me do d theta, 0 to 2 pi, and I'll do my dr last, 0 to 2. And I might work that out to post on the notes that I complete, but let me leave it at that setup for now. Again, using this information, it can be a little tricky. That's what graphing, pardon me, to build those. And trying to draw in some of those columns of volume can be supportive. Okay. All right. I'll write the rest of that problem up, evaluating. If you have questions, concerns, definitely let me know.